for maximum values. Let's just parse that out. So let's let I be a closed bounded interval and f be a continuous function on I. Then the maximum principle should say something like there's a maximum output for this function. So let's see, what should that mean? That should mean there's some input in the interval 0, 1 which produces the maximum output. So there should be some c in the closed unit interval, so that for every x in the closed unit interval, closed interval AB, what should happen? If c is supposed to be the input which produces the max, and x is any input, what should we follow?
Bigger than f of x.
F of c should be bigger than, or maybe equal to f of x.
Yeah.
Yeah.
Are we skipping the other packet that you handed out?
Yeah, so maybe this is a good time for that announcement. So if you look at the webpage, you'll see that that whole packet is actually posted as a challenge problem now. So basically, I just looked at where I was, and all of this stuff can be done from a topological point of view, but I decided that it would take me long enough to build up the framework for that point of view that I'll just do things from a different point of view. So that also means that if you guys like printed off notes for today on like Monday, it's a completely different note packet now. Which also means there might be some more typos. There are some more typos. So if that's what the maximum principle says, what do you think the minimum principle should say?
The opposite?
Yeah, like although inequality should have that. Let I be a closed bounded interval and f be a continuous function on I, then there exists some c in I, such that for all x in I, f of c is less than or equal to f of x. Collectively, those two are referred to as the extreme value theorem. Right, extreme values should either be minimums or maximums, depending on how you want to optimize. And what it says is let I be a closed bounded interval and f be a continuous function on I. Then the supremum of the set f of I and the infimum of the set f of I are both contained in f of I. How do people feel about that? Yeah, and so like this is saying that the superint of the image of a closed bounded interval under a continuous function are both in the image of a closed bounded interval under a continuous function, which is like a thing that I warned you was a really common mistake to make, that people like to just write the supremum of x and assault that it's in x, even though that doesn't tend to happen very often. But this is a set which does have that nice property. And what do you think? Should we say some words about why the, I'll just do the maximum, principle holds as a consequence of that statement? Think that's worthwhile? Yeah, sure. Let's do it. So what does the maximum principle say? It says, let I be a closed bounded interval. We have a closed bounded interval in the statement of theorem 3. So let's let I equal a comma b be a closed bounded interval. Let's let f from I to R be continuous. So, by the extreme value theorem, the supremum of f of I is in f of I. And the same thing with infimum, but I think I'm only going to do it for the one extreme. What does it mean to be in the image of f of I? What does it mean to be in the image of a function?
F of something in your domain equals that thing in your...
There exists a thing in the domain which gets set to that thing. So, by the very definition of image, there exists, I'll use the shorthand, some c in the domain I, such that f of c is equal to the supremum of f of I. Okay, so let's read the maximum principle, since that's what we're trying to prove. This maximum principle says if I is a closed bounded interval, which we have, and f is a continuous function, which we have, then there exists some c and I such that for all x and I, f of c is bigger than or equal to f of x. Have we just come up with a choice of c in I? We have, right? So that's good. We now have to prove something for every x in I. So I guess a good next line is let x be an element of I. Now consider any x in I. There's what I need to prove now, that f of c is bigger than or equal to f of x. What's special about f of c? What's f of c equal to?
The supremum of the f of i's.
The supremum of f of I. Why should the supremum of f of I be bigger than f of x?
Because it's an upper bound.
Because it's an upper bound on the image. Aha. So let's see, since f of x is in f of I, right, because that's what image means, and f of c, well, that's the supremum of f of I is an upper bound on f of I. F of x is less than or equal to f of c, as we claimed. Nice. So the extreme value theorem does in fact imply the maximum and minimum principles. Well, I guess we only proved the maximum principle, but do you think you could do the same thing to get the minimum principle? Yeah, replace soup with in and change some inequalities. So let's see, in here, like all of these are only for closed bounded intervals. Let's see where closedness and boundedness actually comes into play. So here's a function. Let's define the function f from 0 to infinity. Be the function f of x equal to 1 over x. Well, let's see. Maybe I'll like give you guys a choice here. I claim that f of the interval from 0 to 1, excluding 0, including 1, is equal to the interval from 1 to infinity, including 1. What do you guys think? Should we prove that? Maybe we'll at least draw a picture to see why that should be true. What does the graph of f of x equal to 1 over x look like? It's like this function. And I'm interested in what it does over the interval from 0 to 1, excluding 0. And we can just like draw a picture of what the range of this is, right? So it looks like there's the range. There's f of 0, 1. So do you at least like believe the result now, just based on looking at that picture? Which probably you drew better than I did. Okay, but let's just like think analytically for a second. This is a set, right? And that's a set. If you want to show two sets are equal, what do you need to do?
Double integration.
Sure. Yeah, double the two containers. And maybe I'll do like one of them because this isn't the main point of today. I don't know, which inclusion would you like to do?
Let's do the first one.
Okay, let's do the first one. So we want to prove that f of the interval from 0 to 1 is contained in the interval from 1 to infinity. Fair enough. So that means we need to show that everything in the image is in the interval from 1 to infinity. So let's consider anything in f of 1 to 0, 1. I told you there would be more typos. Consider any f in the interval from 0 to 1. I excluded the long endpoint. So, let's see, anything in f of an image, in the image of a function, like that means something. That means there exists something in that set 0, 1, for which f of x is equal to y. what is f of x? What's the definition of this function?
1 over x.
1 over x. So y equals 1 over x. And this x is in the interval from 0 to 1. So what do you know about this x? It's between 0 and 1. And 0 is less than x is less than or equal to 1. Have we proven something about what inverting things, putting them in the denominator, does to inequalities?
Mm-hmm.
Yeah, right? If everything's positive and x is less than 1, then what can you tell me about 1 over x? It's greater than 1. I guess I left off the or equal to, so you did also. Thus, 1 over x must be bigger than or equal to 1. So y is bigger than or equal to 1. Is that exactly what it means to be in the interval from 1 to infinity? Yeah, it is, right? And if you want to go the other way, well, what do you need to do? You need to find an x value, which is in the interval from 0 to 1, with f of x equal to y. But let's see, if you wanted to solve f of x equal to y, I'm not going to do all of it. That's right. Aside, you need to solve f of x equal to y Gesundheit. So 1 over x is equal to y. If you wanted to solve that for x, what would you wind up with? Great. So let x be equal to 1 over y. Then you'll definitely get f of x equal to y. That'll be easy to do. Do you think you can easily show that x is between 0 and 1 if y is bigger than 1? Yeah. So I won't even write anything else down. So let's get to the payoff. Does the extreme value function hold for this function defined over that interval then? That's it. So that's what the image of the function is equal to. Does that set contain its suprema? Does it even have a suprema?
Mm-hmm.
The interval from 1 to infinity? Does that have an upper bound?
No.
No, it has no suprema.
Yeah.
So does the extreme value theorem hold for that function defined on that domain?
No.
No, it doesn't. So the point of this problem was really to prove that closedness was important. Since f of 0, 1 is equal to 1 to infinity, the supremum of f of 0, 1 doesn't even exist.
Can you scroll it up?
Yeah. Which is even worse than just not being in the set. It's not even a thing that exists. People feel okay about that? Yeah. So, in fact, we're happy now? So the secret there is the proof of the extreme value theorem that I'll give. It'll rely on closed and bounded, but not on the word interval. In fact, the extreme value theorem holds whenever you have a continuous function defined on any closed bounded set. And we know what both of those words mean now. We know what bounded means. We just defined what closed means 2 lectures ago. So I'll call such a set compact. And really, this is one of the things that I'm skipping. The word compact has a very precise topological definition, which is much more general than this. In the case of the realignment, they're equivalent. I'll call a set compact if that set is closed and bounded. So tell me why these sets aren't compact. The interval from 1 to infinity, why is that not compact?
It's not bounded.
It's not bounded. The interval from 0 to 1 excluding 0.
Not closed.
It's not closed. It misses a limit point. It misses its limit point at 0. What about the closed interval from A to B? Is that a compact set? Yeah. It's closed. Closed intervals are closed. And what are some bounds on this set? A and B. A comma B give bounds. Maybe just for emphasis, I'll put the above where it belongs. So here's our actual strategy. We will try to prove the extreme value theorem on a closed bounded interval. We'll try to prove the extreme value theorem. To prove the EVT, what will we do? We will prove that f of any compact set contains its sup and inf. All right, if we can pull that off, then we'll be able to deduce the extreme value theorem on the interval a comma b.
Can you explain that one more time? Like why it suffices to show that?
Yeah. So the interval from a to b is compact, and let's look at what the extreme value theorem says. The extreme value theorem says if you have any continuous function defined on a closed interval, then then the supremum of f of that closed interval is in f of that closed interval.
Yeah.
So since the closed interval from a to b is compact, if we know that that is true for every compact set, we'll get that result.
Yeah. Okay.
Yeah.
Okay.
So really what we'll prove is that you could write the extreme value theorem where instead of letting I be the closed interval from a to b, you could let it be any compact set. And in order to do that, I'll need one tool first, because I'll do everything in terms of sequences, which makes sense. What's the definition of what it means? What does it mean for a set to be closed? Maybe we should write these things down. It means it contains all its limit points. In terms of sequences, what does it mean to be a limit point of a set? In terms of sequences.
There's a limit of a sequence which converges to that.
Yeah, it's the limit of a sequence, but then you make it a little bit more precise. There exists a sequence, x of n, of elements of k, differ from x, such that x of n converges to x. So we have this nice sequential definition of limit points. And I guess the other word we see all around is the word continuous. What does continuity mean in terms of sequences?
For every sequence of elements of k that is not x, I believe.
No, you don't need that.
Oh, okay. Whenever xn converges to x, it follows that f of xn converges to f of x.
Yeah. So the sequential definition of continuity is just that continuous functions respect limits of sequences. Right, that's all that says? So that's what we'll really use, and we'll do everything in terms of sequences. So let's get compactness in terms of sequences. So here is a reformulation of compactness as a single property that just has to do with sequences. Let's let K be a subset of R. I'll call my compact sets K for compact, as long as you spell compact with a K. If K is, let K be a subset of R, K is compact if and only if for every sequence x sub n of elements of K, there exists a subsequence x sub n sub K of x sub n, which converges to an element of K. So this is like a combination of the result of like the Heine-Borel theorem with closedness, which maybe makes it super believable, because what do you need to use? No, Bolzano-Weierstrass. What do you need to use the Bolzano-Weierstrass theorem? What do you need to know about the sequence? No, just rounded down. That's Montreux convergence. So just like whenever a sequence is bounded, you know it has a convergent subsequence. What this says is if the sequence, even better, is a sequence of elements of a compact set, the limit is still in that compact set. So that's like closedness does that. So it's really believable that this theorem should be true. Which I guess is good because we're about to prove it. So let's do it. Let's let K be a subset of R. Let's do the forward direction. So let's assume that K is compact. So what two things do you know about K because it's compact? Every compact set is
Closed.
And closed and bounded. Check out the statement of the theorem. What is it that we need to prove about this set?
For every sequence x of elements of K, there exists a subsequence x n of K of x n, which converges to an element.
For every sequence x sub n of elements of K, x sub n has a convergent subsequence whose limit is in K. That's the same as what you said. Maybe the words are different. I just noticed that I didn't give myself enough space to write all the words you said. So I chose to write something slightly shorter. Right, that's equivalent, right? Okay, so we need to prove something about every sequence of elements of K. So we've got to start by considering an arbitrary sequence of elements of K. So as a first step, right, I said Bolzano-Weierstrass before. We need to find a convergent subsequence of this sequence. The only tool I know that does that is Bolzano-Weierstrass. To get Bolzano-Weierstrass, I need the sequence to be bounded. Why should the sequence be bounded?
Because K is bounded and it's a sequence of elements of K.
Because K is bounded and it's a sequence of elements of K. That should mean that the whole thing is bounded. How much more detail than that do you guys want? You want more detail than that? Okay, well, I'm going to give you more anyway. I mean, that is all of it. K is bounded. Let's let U and L be bounds. Then, let's see, for all n in N, x sub n is in K. So, L is less than or equal to x sub n is less than or equal to U. So L and U are bounds on xn. So it's bounded. All right, that's exactly what you said, right? This is why every sequence of elements of the bounded set is bounded. So the set is bounded. The sequence is bounded. What does Bolzano-Weierstrass tell you about bounded sequences?
Convergent subsequence.
There's a convergent subsequence. There is a convergent subsequence x sub n sub k. Which I guess, like, I did put a blank there to write that on, but it went on to the next page. It's that blank. So let's let x sub n sub k be that convergent subsequence, and let's let x be the limit of that convergent subsequence. We're basically done, right? we have almost everything we need. Did I flip that too soon? Should I go back? Okay, I go back. So we found a convergent subsequence. What's the only other thing we still need to prove the theorem?
Its limit is in K.
We need its limit to be in K. We can talk about its limit because it's convergent, so it has a limit. So let's do that. Let's prove that the limit of this convergent subsequence is in K. So it's that x sub n sub k be the convergent subsequence above, and x be its limit. We're almost done. We only need to show that x, the limit of this convergent sequence, is in K. That's all we still need. Everyone buys that that's all we need to be done with this half of the proof? Okay, good. So let's suppose for the sake of contradiction that this x is not in K. Let's see what we have then. Let's see, each of these x sub n sub k's is in K, right? Because x sub n is in K for all n. It's a sequence of elements of K. While x is not in K. Could x sub n sub k possibly be equal to x at any point though? Yeah, it can be. They're in different sets. So these two things are not equal. Aha. So let's see. Have we just found a sequence of elements of K different from x, which converge to x? We have, right? So we have found a sequence, x sub n sub k, of elements of big K, which converge to x, but are never equal to x. By the sequential reformulation of a limit point, then, what can we conclude? X is a limit point of K. X is a limit point of K. So let's see what we have then. X by assumption right now is not in K, but X is a limit point of K. Have we just shown that the set is not closed? Does it fail to contain one of its limit points now? But we assume that the set was closed, so there's a contradiction. As x is a limit point of K, K is not as x is not in K and x is a limit point of K, K is not closed. This contradicts the assumption that K is compact. Therefore, it must be that x is in K. So why does this prove the forward implication of this claim? Well, let's see. Did we consider an arbitrary sequence of elements of x sub n? So let's see. We have shown now that for every sequence of elements of K, what did we show exists for this sequence of elements of K?
The subsequence whose limit is in K.
For every sequence of elements of K, there is a subsequence whose limit is in K, as we claimed. Let's do the opposite implication now. Let's assume that for every sequence of elements of K, there is a convergent subsequence whose limit is in K. And we must show that K is compact. If we want to show that K is compact, then what two things do we need to show about K?
Closed and bounded.
We need to show it's closed, and we need to show it's bounded. Let's prove that it's bounded. And how will we prove it's bounded? Well, let's suppose it's not bounded. And in fact, not being bounded means either the set is not bounded above or it's not bounded below. Let's just assume it's not bounded above. The not bounded below will be like the same game. So let's suppose K is not bounded above in particular, if we consider any natural number n in big N, is that natural number an upper bound on the set K? If it's not bounded above, could n possibly be an upper bound?
No.
No, it doesn't have any upper bounds. N is not an upper bound. But wait, so let's see if we can even just do this in our head. If little n is not an upper bound on the set K, what does that tell us? What can we deduce as a consequence?
There exists some k in K such that, or well, there exists an element of K which is bigger than that.
There exists something in K which is bigger than n. And I'm going to, I mean, K is a fine name for it. I'm going to, like this thing that we're building depends on the choice of little n, right? Different choices of little n will have to produce different values for this thing that demonstrates it's not an upper bound. So I'm going to call it x of n. There exists some element x sub n in K such that x sub n is bigger than little n. Have we just produced a sequence of elements of K? But what do we know about every sequence of elements of K?
There's convergent subsequence.
They have convergent subsequence. They have a convergent subsequence. Yeah. So let's see then. By the thing that we assumed, which was labeled as 1, I'm going to call it 1 from now on. X sub n has a convergent subsequence, x sub n sub k. But tell me, what can you tell me about the limit as n goes to infinity of the sequence that's always equal to n?
No, well, no.
It's infinite, right? It diverges to infinity, which is a very special kind of divergence. So the sequence n diverges to infinity as n goes to infinity. And we know right now that x sub n is strictly bigger than n for all n. So what can you tell me about the limit as n goes to infinity of x sub n? It's also infinite. It also diverges to infinity. Now let's think about that subsequence we just cooked up of this sequence x sub n. What can you tell me about its limit? If x sub n goes to infinity, then what can you tell me about the limits of these subsequences?
They also go to infinity.
They're also all infinite. But wait, did we just show that x sub n sub k does not converge? Right, it diverges to infinity. We said it converged. Is that a contradiction? There we go. So k must be bounded, because that's what we assumed in order to get this contradiction. Let's show that this set is closed. So let's assume that P is a limit point to k. If we hope to show that k is closed, what do we need to show?
Contains all its limit points.
It contains all its limit points. Yeah.
I have a question.
Yeah.
So, because x sub n goes to infinity, that's how we know the subsequence goes to infinity? We just know that.
Yeah. So do you remember when we proved that if a sequence converges, then all of its subsequences converge to the same thing?
Yeah.
Same thing.
Okay.
You would consider any big n, since x sub n goes to infinity, then eventually x sub n is bigger than that big n. But like n sub k is always bigger than k, so if little k is bigger than big n, bigger than whatever threshold you needed to cross it, x sub n sub k is also bigger than big n. So it really is the same one. I guess it is a legitimate point. We haven't literally proved that claim. It's only believable, right?
Yeah.
So let's get to close now. So let's set P be a limit point of k. As Tyler said, a set is closed if it contains all of its limit points. So if we just consider an arbitrary limit point, what do we need to prove if we want to show that k is closed?
It's in K.
We need to show that that limit point is in k. Okay, but let's see. We have the sequential reformulation of limit points. Since P is a limit point, what do we know of k? What can we deduce of this conclusion? We can deduce that there exists a sequence x sub n of elements of k, such that, well, I guess x sub n is not equal to P for all n, and x sub n converges to P. Right, that's what it means to be a limit point in terms of sequences. You can find a sequence what converges to it. So maybe I'll just, those are the things that we'll need. X sub n is in K. It is different from P. And the sequence X sub n converges to P. But remember, this set is compact. K is compact. What do we know about sequences of elements of a compact set? Nope, nope, nope. What did we assume about sequences of this particular set?
The limits are in K.
Yeah, not only that, but like their limits exist in some sense.
Yeah.
We can use the assumption labeled 1, this assumption. Every sequence of elements of K has a convergent subsequence whose limit is in K. So, assumption 1 implies that there exists a subsequence x sub n sub k such that x sub n sub k converges and its limit of x sub n sub k is in the set big K. Right, that's exactly what we assumed about every sequence. Well, let's check out the definition. By the very definition of x sub n, what's the limit of x sub n?
P.
P. So what's the limit of x sub n sub k?
P.
But we assume that the limit of x sub n sub k is in the set big K. So what can we conclude? Have we just shown that this set is closed? Because we showed it contains all of its limit points. As we just showed that every limit point of K is in K, K is closed. We've proven that K is closed and bounded, ergo it's compact. So now we're ready to prove the extreme value theorem on compact sets by using this tool. There will be 2 steps. The first step will be to prove that if you have a continuous function on a compact set, then its image is still compact. And the second step will be showing that the supremum and infimum of a compact set are both in the compact set. So I think I can do this in 10 minutes. And I have a little bit more than 10 minutes. I should be fine. So let's let K be a compact set, and f from K to R be a continuous function. We have to show is compact. We have to show K is compact. By the theorem we just proved, what do we know about compact sets? By the theorem that's not theorem 1, but actually theorem 5. I don't know why it said theorem 1. Like I screwed up something in my tech.
Every sequence of elements of K has a limit which is in K.
We know that every sequence of elements of K, we have to show that f of K is compact. So we have to show that every sequence of elements of f of K has a, in fact, let's use this word that we've not used today yet, has a subsequential limit which is in K. Everyone happy enough? So let's just, so we have to show something about every sequence of elements in f of K. Let's let y sub n be any sequence of elements of f of K. We have to show that y sub n has a convergent subsequence, y sub n sub k, such that limit of y sub n sub k is in the set f of big K. Right, if we can show that, then we'll be done. So let's play the game. So here's the strategy. I don't know that f of k is compact. I know that k is compact. So let's try to get a sequence of elements of k instead. Let's see if yn is in f of k. Well, what does it mean to be in f of k?
Wait, Dr. David?
Yeah.
So the green, so you say every sequence of elements of f of k as a subsequence whose limit is in f of k, right?
Yes.
Oh, okay. Okay.
Yeah, that absolutely would be like a nonsensical thing to say.
Okay.
F of k and k aren't even, those don't need to like intersect at all. Those could be disjoint sets. They don't have anything to do with each other. So let's try to go from a sequence of elements of f of k to a sequence of elements of k. The fact that y sub n is in f of k tells you something, right? What does it mean to be in the image of a function? There's something in the domain what maps to it. So, there exists something in the domain which maps to it. There exists some x sub n in k, such that f of x sub n is equal to y sub n. And notice, different choices of n will result in different choices of y sub n, so you'll need different choices of x sub n. So this x sub n really is a sequence. Putting a little n in the subscript really is appropriate. Have we just constructed a sequence of elements of k? Yep. Which is compact by assumption. So by this sequential compactness theorem, what do we know about the sequence x sub n?
It converges to something that is in f of k.
We know that k is compact. So this is a sequence of elements of k. Like you put an extra f of in what you said.
Oh, yeah, xn. Yeah.
So we see that x sub n has a subsequence which converges to an element of, what should the limit be in? What set do I know it's in? Okay. So let's let x sub n sub k be that sequence above, and x, which we now know to be in the set big K, be its limit. So here's what we'll do now. I need to show that this, I've gone a fair distance from my original goal. My original goal was to study the sequence y sub n. I just said something about x sub n. But x sub n and y sub n, they have something to do with each other. So let's actually just use properties of continuity and study f of x. So f of x right now, by its very definition, is f evaluated at the limit of x sub n sub k, as x is the limit of x sub n sub k. But by the sequential definition of continuity, this one, evaluating f at a limit is the same as what? Yeah, what this says is, well, let's reformulate it a little bit. This says that the limit of f of x sub n is equal to f of x, which is the limit of x sub n. So tell me, what is f of the limit of x sub n sub k?
Limit of f of n sub k.
Yeah. By sequential continuity. But recall for me, this x sub n sub k has something to do with the sequence y sub n. What is f of x sub n sub k equal to? Or maybe better, what is f of x sub n equal to? How did we choose this sequence? So what is f of x sub n sub k equal to? since f of x sub n sub k is equal to y sub n sub k. Hey, cool. Have we just produced a convergent subsequence of this sequence y sub n? That's good. So we've produced a subsequence y sub n sub k, which converges to f of x. But in order to show that the set f of k is compact, we need a little bit more than that. We don't just need it has a convergent subsequence. We need that convergent subsequence to have its limit be in f of k. The limit of this y sub n sub k is f of x. Is f of x in f of k? Yeah, it's equal to f of something in k. By the definition of image is in f of k. Maybe I'll put like a line here saying something like as little x is in big K. People feel okay about that one? Yeah. Why does this show f of k is compact? Well, what did we do? We considered any sequence of elements of f of k and showed that there is a convergent subsequence whose limit is in f of k. Thus, by this formulation of sequential compactness, f of k is compact. And maybe I'll even say, like, I alluded to like a very topological notion of compactness. This sequential compactness is something that follows from compactness. In truth, there are, I don't know, a half dozen different variants on the notion of compactness in the world of topology, which all have different names like quasi-compact or pseudo-compact, strongly compact, weakly compact, weakly quasi-compact.
That must get confusing.
Yeah, I mean, you pick the one you need to walk with, and use that. Which are all slightly different from each other. In the case of the real line, they're all equivalent. So, the last thing we need. Let's let K be a compact non-empty set. Then the supremum of f of k and the infimum of k each exist in our elements of k, is what this next theorem will say. Maybe instead of doing that right now, let's actually prove the extreme value theorem. That was my goal to begin with, and I think I can do that in the 2 minutes I have. So let's prove the extreme value theorem. Let's let I equal to AB be a closed bounded interval, and f be a continuous function defined on I. I need to show that the suit of f of I and the inf of f of I are both in f of I. But tell me, is I compact?
Yeah.
Yeah, it's a closed bounded interval. I guess we observed that on page 2. We see that I is compact. But wait, I is compact, and f is a continuous function defined on I. So by the theorem we just finished proving, what can we conclude? Yeah. And by the theorem, which apparently I won't be proving today, that means that the supremum of f of I and infimum of f of I are both in f of I. Hey, is that exactly what I needed to prove to conclude the extreme value theorem? So really what I did is I introduced this notion of a compact set. I proved the compactness is preserved under continuous functions. And I proved that, well, I didn't prove that. Compact sets contain their suits and ins. And given those two facts, the proof of the extreme value theorem over a closed bounded interval just became abstract nonsense. Like if you can't use this theorem, use that theorem, but you didn't have to do anything. So, what will happen next time? I think what will happen next time is I'll prove that theorem sets an ICAM. So if you like to read through that, you'll probably be able to follow that theorem pretty easily on your own. And then it'll be a group walk day in which you'll prove that. How many people know what Cantor's set is? How many people have heard of Cantor's set?
I've heard of it, but I don't know what it is.
The Cantor dust, the Cantor tonary set. Okay.
Is that like that fancy hand?
That's like the boss middle,
Oh, okay.
which has to do with other stuff you can't possibly. You'll prove that that thing is compact, and so the extreme value theorem holds over Cantor's.
Are we turning in homework?
Oh yeah, homework. I always forget about homework. And I guess anything else that you guys want to want in, and benchmarks are getting slightly chaotic, but that's okay. These are the devils?
You should have been first. Oh, I was like, wait, what?
Yeah.
Like I say, that's not good job. Yeah.
Okay.
Off to topology. Aren't you so excited like I do? Another day.
So if I'm thinking clearly, I think we're starting using metric spaces maybe
Probably, yeah. I
Where
think
like, thank you.
that's what Carolyn mentioned.
If you want to like straight up try to extend all of the notions of analysis, metric spaces are where you need to go.
Okay. Neat. Well, I'll see you later.
See you.
These are extras.
Yeah.
Can I follow you upstairs and ask you a question?
Yeah, absolutely. What about?
Homework.
Okay. I guess you don't even need to follow me upstairs. You know where I'm going.